Hello everyone, I'm Cedric from MTPI and I will be your host for today. Welcome to the first live session of the first electronic conference on Universe. This e-conference is hosted online from the 22nd to the 28th February 2021 and is organized by MTPI and the journal Universe. I would like to thank the conference chair, the conference committee, and the session chairs for making this e-conference possible, along with the speakers and, of course, our attendees. I would like to remind everyone that this session is recorded. The recording will be made available as soon as possible and will be posted online alongside the 3 other live sessions of this e-conference. This webinar is also being live streamed on MTPI's YouTube channel. Hello to those of you watching us on there. Today's live session is chaired by both Dr. Magdalena Kersting and Professor Dr. Matteo Luca Ruggiero. Dr. Magdalena Kersting is an educational researcher, physics educator, and science communicator working to bring great science education to as many people as possible. Currently, she works as a postdoctoral researcher in a project called Linking Instruction in Science and Student Impact to develop a framework of embodied cognition in science education and to study the quality of instructional practices in science classrooms. Previously, she developed a digital learning environment about Einstein's general theory of relativity as part of ReLI-Quant. She has a lifelong goal of getting students excited about modern physics, and she collaborates with the Einsteinian Physics Education Research Collaboration and the IRC Center of Excellence for Gravitational Wave Discovery to make that happen. Professor Dr. Matteo Luca Ruggiero teaches physics at the ITES in Turin, Italy. In a previous life, he graduated in physics at Università di Pisa, and then he got a PhD in theoretical physics at Politecnico di Torino, where he also worked as a postdoc student and as a contract professor. He also collaborated with the University of Turin, and he is research associated at the INFN, the National Institute for Nuclear Physics. His main area of interest pertains to the study of rotation effects in relativity in different contexts. Thank you to both of you for chairing this session. There will be 2 presentations today given by Professor Dr. Daniel Whiteson and Professor Dr. Ute Kraus. Each presentation will be followed by a Q&A session moderated by our session chairs. If you have any questions, please feel free to post them in the Q&A box at the bottom of your screen, and please not on the chat. If you wish to ask your question in person, please raise your virtual hand and I will hand you the microphone. That's it from me. Now it is time that I hand over the microphone to our 2 session chairs. Thank you and enjoy, everyone.
Thank you for the introduction, Cedric. Welcome, everyone. It is great to see you, and it's my absolute pleasure to welcome you to the first physics education session of the ECU 2021 conference. I see many familiar names, although I don't see your faces just yet. But for those of you who don't know us, we have been an active community trying to promote modern physics education or Einsteinian physics education. And we really try to modernize and transform physics education and working jointly with physicists, educators, and teachers. And what has come to all of our efforts is that we want to provide a modern and relevant educational experience to physics students. And over the past years, we have always managed to meet somewhere in this world, in Australia, in Germany, in Norway. And today, even more can join from all around the world. So as Cedric just said, we have 2 keynote speakers today. Daniel and Ute, and on Thursday we are following up with 3 more awesome keynote speakers. And then on Thursday, our Australian colleagues will be able to join as well. I think that's it from me now, and I give it to Matteo to introduce our first fantastic keynote speaker.
Thank you, Magdalena. Well, it's a pleasure for me to introduce Daniel. Daniel is a professor of particle physics at the University of California, but he's here because he is doing a lot of things to explain modern physics using different languages. For instance, together with Jorge Cham, they are the author of a very popular podcast, Explain the Universe, where they try to explain in a simple way the mystery of the universe, and also in a funny way. Also, they are the author of an international bestseller book, which is called We Have No Idea. I think you all need to read this book if you want to teach physics, modern physics, in a simple and interesting way. Eventually, he is also a co-creator of an animated series on PBS Kids, which is called Eleanor Wonders Why. Again, the topic is here catching children's curiosity, stimulate them to ask questions and to try to answer using a science inquiry skill. So I think that Daniel is the right person to start our discussion. So welcome, Daniel, and we can start. Thank you.
Thank you very much. Thank you for that wonderful introduction. And thank you to everybody who is here to listen to us talking about physics and how to share the wonders and the joys of physics with everybody. All right, so let me just share my screen here. So welcome everybody. I've been asked to talk about teaching physics with comics, and this is something I'm really excited about, and I do with my friend and my longtime collaborator, Jorge Cham, who you probably know very well. First, I want to make sure you understand where I'm coming from. My path to physics education and teaching physics to people is really from the research direction. That is, I'm a particle physicist. I work at the Large Hadron Collider. We smash particles together to try to understand the nature of matter at its smallest scales and reveal the fundamental structure of the universe and all of that stuff. But part of my job, of course, is teaching. And so I teach students at UC Irvine. And I want to avoid making the mistake that a lot of physicists make, which is that they think that because physics is a foundational science, that everything derives from physics, and that if you're an expert in physics, you're therefore an expert in everything. And that's certainly not the case. And even when it comes to things related to physics, like teaching physics, most physics professors have no formal education or training in education. They're just thrown into the job because you're a good researcher. They expect that you can also manage to do teaching. Now, I happen to be very interested in teaching, but I don't claim to be an expert. I dabble in education research. I work with folks who do have a formal training in education and have read the literature. So it's something that's very interesting to me, but I'm not an expert. So today I'll be telling you about my experience and my journey in learning how to teach physics to people using cartoons and comics, especially modern physics or Einsteinian physics. But I don't claim to be an expert. So thank you to all of you who are doing research and helping us understand what actually works, what actually teaches people, what people actually enjoy, so that you can help us practitioners, us teachers, actually get these ideas into the heads of students in a fun way. Because I am passionate about teaching physics to students at UC Irvine, but UCI is a public university. It's paid for by the public. And so I feel also an obligation and an opportunity to teach physics, not just to the students at UC Irvine, but to everybody, because there's a vast community of folks out there who would benefit from understanding physics a little better, and also who have a real interest. Physics is not something which is just, physics questions are not questions just asked by people in academic departments. Everybody wants to know the answers to questions like, what is the universe made out of and how did it start? So there's a huge appetite out there for people to understand physics. So today I'll be talking mostly about teaching physics to the general public, to everybody who fashions themselves a physics student, even if they are not formally set up. And there are also folks out there who need to understand some physics, even though they may not understand, they may not appreciate the importance of it. Some of these folks are very important people in our society. Here, for example, is a clip from the United States Senate.
We have forgotten because we keep hearing that 2014 has been the warmest year on record. I asked the chair, you know what this is? It's a snowball. And that's just from outside here.
So people at the highest levels of government in the United States of America don't understand the distinction, for example, between climate and weather. Basic knowledge in physics is very important. A basic understanding of the scale, the structure of the universe is also vital. Here, for example, is my former representative in the US House of Representatives from Orange County asking a question of a scientist. Listen.
For 1 minute for this question. That is, you have indicated that Mars was totally different thousands of years ago. Is it possible that there was a civilization on Mars thousands of years ago?
So the evidence is that Mars was different billions of years ago, not thousands of years ago.
Well, yes.
There's no evidence that I'm aware of.
Would you rule that out? There's some people. Well, anyway.
I would say that is extremely unlikely.
Okay. Well, thank you all. Thank you, Mr. President. Thanks for the good job you do.
And so it's terrifying to me that the folks making life and death decisions about our country and our world have such a little understanding, such a shallow understanding of basic concepts in physics and in cosmology. And we've all seen the impact of this very directly this last year when folks who are in decision-making situations do not have a grasp for the basic concepts of science and do not respect them. And so I think it's very important that us scientists learn how to educate everybody about basic concepts in science and in physics. And so let's talk for a moment about how this usually happens. Like, we figure out something at the Large Hadron Collider, we learn something interesting about the nature of matter, or scientists use telescope to understand a black hole. What then happens? Well, usually the typical way scientists communicate is by writing scientific papers. So they'll write a paper, and then maybe sometimes it's picked up by the university, which issues a press release if they think it's exciting. And then sometimes a reporter might decide this is interesting. And if they can convince their editor that it's actually something we're talking about, then maybe it gets into a magazine. And perhaps it gets released on the internet or on other media. And then that's where the public pick it up. So it's a lot of steps between the actual scientist, the actual words being written by the scientist about the universe, and folks in the public hearing a description of it. And that's why you get descriptions of science that are sometimes very misleading or easy to misunderstand. There are these awesome projects where people are using quantum entanglement to do quantum teleportation of information across vast distances. But if you read this headline, scientists just successfully teleported an object into space, you might get the impression that they took a rat in a lab and they teleported it into space, right? If you didn't understand the science behind it already, you would have no way to understand the meaning of this article, and you were likely to be misinformed. Now, this is written by, a paper in the UK, which doesn't specialize in science, but also sometimes organizations like Symmetry Magazine, which specializes in writing about particle physics, can propagate popular science ideas which are more misleading than informational. A lot of folks like to talk about how space inside the atom is mostly empty because particles are very, very small and the distances between them are large. But of course, that space is filled with energy. It's filled with forces that create that volume. So I think that's more misleading than informational. And popular science scientists and science communicator Sean Carroll agrees, right? That people need to think about science a different way rather than propagating this sort of misinformation. Sometimes I read popular science articles about my own field. For example, here is some of the coverage of the discovery of the Higgs boson, which is an actual science event that I participated in on the ground. And I read the New York Times article about it, and in which Dennis Overby wrote that the collective efforts created the Large Hadron Collider and have revealed the deepest layer of reality our species has ever probed. That's like nice poetic writing, but I don't even really know what it means. And I'm a scientist who worked on this project. So, what is the deepest layer of reality? And more broadly, you see that a lot of science writing makes pretty basic mistakes about how science works and how to interpret it, sometimes with important consequences for how people make decisions in their lives. Here's a study, for example, that was reported on in the New York Times that showed that there was a correlation between the number of books in your house and the grade level reading performance of your children, right? There's a correlation. And they come right out and say, owning books in the home is one of the best things you can do for your children academically. As if, you shouldn't go and spend time reading with them or do all the things that make these children have success in reading. Just go out and buy a bunch of books and fill your bookshelves with them, right? Like they say it straight up, they say, they of course acknowledge that maybe there are other things you can do as well, but it doesn't take away from the fact that they directly say that this is one of the best things you can do for your children. And we all know that correlation and causation are not the same thing. You can find easily many examples of things that are correlated that have no causal effect. There's a shocking correlation, for example, between the number of sociology degrees, PhDs awarded in the United States and the number of non-commercial space launches over 10 years. It's sort of incredible. And so if you follow that same logic and you wanted to encourage non-commercial space launches, you might pour funding into sociology doctorates, right? But there are more examples of this when it comes to people's health. Here's an article that says that drinking a cup of coffee may add 9 minutes per day to your life, based purely on correlation, right? People who drink coffee tend to live longer. There's no understanding in this article of what's making people live longer or why they're doing that. And they say very directly here, if you like to drink coffee, drink up. If you're not a coffee drinker, then you need to consider if you should start, right? People make decisions based on this misunderstanding. And so it's important that people understand not just the physics and not just the science, but also the critical thinking of how to read these things, how to digest this information. And sometimes the clearest science communication is written by parody magazines, right? Here, The Onion kind of gets the science totally right. It is true that accidental heroin overdoses could be prevented with less heroin. This is trivial and obvious, but it's actually more accurate than most of the science writing that I showed you here today. And so it's frustrating to me as a scientist when I see misinformation in general media, and also when I see our science portrayed as hard to understand or difficult to digest or out of the realms of the kinds of things that everybody who's excited about science could actually understand. Here's a cartoon by Roz Chast in the New Yorker, and look at this last panel. If I concentrate ultra hard, will I ever be able to understand the Large Hadron Collider? No, right? Don't even waste your time. And so to me, that's frustrating. And this is the kind of thing that motivates me to say, let's see how we can explain this to folks. What is possible to accomplish in terms of teaching these cool, awesome ideas to everybody out there who is interested, and also people out there who may not realize that they need to know a little bit about it. So why is it so difficult for scientists to effectively communicate directly with the public? It's not like scientists don't do a lot of communication. In my fields, for example, there's a conference or 2 conferences or 3 conferences every week. Scientists are constantly talking, right? And specifically in particle physics, a typical day in the life of a particle physicist starts with meetings and meetings and meetings and meetings. Everybody is talking to each other constantly. The number of PowerPoint slides presented every year is growing exponentially and rocketing towards infinity. And inside these meetings, scientists do a good job of communicating their ideas to each other, right? Here inside a subfield, we have a very specific language that we all have been trained to understand and we can use to talk to each other. So if we understand exactly what these labels mean, MPT, PTVH, whatever, then we can get some information if we are all trained in the same language. But it turns out that scientists have trouble communicating their research effectively to the public, but also even to scientists in other related fields. For example, I do particle physics research, but I collaborate a lot with folks in machine learning. And it turns out that we use different words to describe exactly the same topic. So the exact same mathematical concept described using different words. And so if you want to speak to people, even in another discipline in academic research, you need to learn to speak basically another scientific language. And so this is the challenge, I think, that we have to overcome, is learning to speak the language of the folks who you're teaching. The folks who are receiving your information, you have to talk to them in a language that they can understand, not in a language that makes sense necessarily to you. So I was thinking about this science news cycle and how there's so many steps to get between the scientist and the public, and then along the way, sometimes the information is lost or even misrepresented. So I started asking myself this question: can scientists teach physics to the public? Can we reach out directly and learn how to communicate with the broad public to teach them in a way that they can understand and appreciate? So I started to look around to see what had been done. And there are a lot of examples. Here, for example, there's a very nice blog written by another particle physicist, Tommaso Dorigo, where he takes a science paper and he breaks it down and he talks about it. And it's very relevant and it's very accurate, but it's also still very technical. Like, I think you need to be a PhD physicist to understand what he's talking about. Other folks sometimes just sort of seem to make it work. Here's a very popular, for example, science outreach effort from the Large Hadron Collider you might have seen.
Oh yeah. I'm about to drop some particle physics into club. The LHC is super duper fly. You know what I'm saying. Check it.
And so that was very popular. You see there are 8 million views there. And so why did that work? Why did that get so much attention? Well, we don't quite know. And it's fun, certainly, but not everything that's fun, that's exciting, that's clever gets attention. For example, they followed it up with another rap about black holes, not nearly as much attention. And we all know that what gets attention on the internet can be kind of random. Here, for example, is a very, very popular and famous video. And you notice this one got 12 million views, right? 4 million views more than the LHC rap. So it's difficult to predict, or sometimes even to diagnose, what works on the internet. And then there are folks who are very popular science communicators, and sometimes what they're doing is a little bit more politics or sociology than just pure science. They're sort of advocates for science as an institution. And then, of course, there are lots of excellent communicators who are doing a good job. It's Carl Sagan, of course, Katie Mack, physics girl Diana Cowan, lots of folks out there really making it work and communicating science to the general public. So what's the common thread? What really makes it work? Well, I think I already gave away my idea, which is that in order to communicate with folks, what you really need to do is learn to speak their language, learn to give it to them in a way that they can digest, that makes sense to them. That's the essence of teaching. And in my view, is, again, not formally educated, but in my experience, you need to take the ideas and download it into somebody's brain in a way that they can receive it. So when I was at UC Irvine and assigned to teach as a young professor, one of the classes I was first given was special relativity, which is super fun to teach. Love blowing the minds of young scientists when they learn about this stuff. And I found special power in using visual aids. A lot of these puzzles about special relativity, a lot of the apparent paradoxes, the contradictions, are really clarified when you can lay everything out using geometric and visual descriptions of complex ideas. So for example, a space-time diagram is very helpful for understanding time dilation effects. And I found these wonderful, basically cartoons drawn by Tatsu Takeuchi. He's an associate professor of physics at Virginia Tech. And he has these really wonderful little cartoons, each of which is very nicely laid out and has little folks sitting on each one to help you understand what's happening. And with a single space-time diagram, you can explain a really complicated topic like time dilation, or here, for example, is his explanation of the twin paradox. Everything laid out in one nice diagram that's easy to look at and easy to digest. And so and there's a dash of silliness, there's a dash of whimsicalness in his presentation that I thought was really powerful. And later that year, I read an online technical comic. This is a comic by Scott McCloud that describes the origin of the Google Chrome browser. And, you know, as dry a topic as how to write a browser is, this comic was really fun to read. It was really interesting. It took complex technical topics and it laid it out in a clear way. There was humor. Obviously, the art is very nice. And so I started to think, wow, wouldn't it be cool to use comics to teach physics, to somehow use comics to reach out to people everywhere who were interested in these questions, but weren't able to really digest a lot of the other science communication that was out there. But I'm not an artist myself, and I didn't have time or the energy to draw these things myself. And so I thought, who could I get to do some drawings? Who could I get to illustrate some physics cartoons? And so my wife, who's also an academic and a fan of PhD comics, she said, well, why don't you write to Jorge Cham of PhD Comics? He's a good artist and he knows some science. And, you know, everybody out there knows that Jorge is sort of a celebrity in academia. And I thought this is sort of like emailing Brad Pitt and asking him to do a movie about yourself or join on your movie project. But I cold emailed him, and amazingly, he wrote back and said, yeah, let's do it. Let's work on a project. So for those of you who don't know him, Jorge is the creator of this very popular strip, PhD Comics, and it's all about life in academia, how frustrating the experience is of research. And it's very popular. It's seen all around the world, many thousands of universities. And the main character is a Jorge-like character who's struggling to get through graduate school and has a grumpy advisor pushing him everywhere. And he really has captured sort of the essence of what it's like to be in graduate school, you know, the struggling with procrastination, with getting things done, the difficulties of working on research and not necessarily having it always go well in your relationship with your own research. So he's definitely got a sense of humor and he knows how to draw. In addition, he had departed a little bit from his comics, which was writing about the grad school experience, and started writing about people's research, talking about why they did it, talking about how they got there, humanizing it, talking about, you know, what motivated people to do science, why they were excited about it. And so I worked with Jorge and we worked on a cartoon talking actually about the Higgs boson. And so he came down to UC Irvine. He lives in Pasadena, just an hour or so away. And we spent an afternoon talking about physics and the Higgs boson. You can see there's a drawing of me waving my arms as I explain something to him. And we originally just intended just to make a comic book, like something which is a physical thing that you could hold. But Jorge had the idea, he recorded the audio of me explaining the physics to him, and then he edited it down and decided to illustrate it. And so here's a little snippet of the video that we produced together.
So one of the things people predict is the Higgs boson. The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things that have mass means it has stuff to it. It's not actually stuff. Earlier I was saying electron has mass, but has no volume. How can that be? Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons, some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Interestingly, you can't have negative mass.
So that was the video. And the video did very well. It went out all over the internet and it got a lot of coverage. And folks were saying things like it was one of the clearest explanations of the Higgs boson they had seen. And people really appreciated, I think, having a way to grapple with this topic, which was everywhere in the news, but didn't always get explained in a way that people could understand. And so that was very gratifying to see that people were getting to understand this. They were getting to appreciate it. They were getting to really experience the excitement of the discovery of the Higgs boson. And so since then, we've collaborated on some other projects. We have a book out called We Have No Idea that I'll tell you a little bit more about in a moment. We do a podcast twice a week called Daniel and Jorge Explain the Universe, where we talk about all the complicated topics in physics and answer questions from people all around the world. And now recently we have a television show encouraging about a little bunny rabbit that's very curious about the world and wants to understand the world around her and learns to ask questions and use science to answer them herself. But the topic that, but the comics grew into this book, and the book is sort of unusual from the point of view of a popular physics book. Most popular physics books tell you what we have learned about science, what we know about the universe, all the incredible bonkers things that are going out there in the universe. But we wanted to write a different book. We wanted to write a book about all the things that we don't know about the universe, because we wanted to connect to what I thought was this misunderstanding in the general public that most of the exploration out there has been used up. When I was a kid and I was reading about the Age of Explorers and I was learning about people sailing to new continents or making rafts and finding islands where no human had ever landed, I thought that was really exciting, right? I wanted to be the first person to do something. I wanted to be the first person to walk on a beach, the first person to eat a new fruit, right? To be on the forefront of human knowledge. Imagine what it must have been like to be the first person to ever eat chocolate, right? There was a first person, or the first human being to see the Grand Canyon. Wow, what a moment. Or, the first person to see the Grand Canyon while eating chocolate or whatever. These are all firsts in human history, and I was really excited. But as you read about the Age of Explorers, you sort of get the idea like, it's kind of in the past, right? Thanks to Google Earth and satellite technology and all this stuff, we've explored a lot of our planet. We know a lot about what's going on out there on Earth, at least. And people have the impression that science has the universe mostly figured out. I mean, you look at what technology has achieved, right? I mean, we have airplanes that can take you around the world in just hours. You can download all of human knowledge into your pocket. It's even fast food chains are, innovating technologically on the kinds of junk food that you can buy. And so we wanted to communicate in our book that the opposite is true, that it's not true that most of science is figured out. It's not true that there's nothing left to learn, or even just that there are just a few details left to wrap up. We wanted to communicate that there's a huge amount of exploration left to do, that most of science, most of the journey of physics has not yet been completed. And we wanted to do this because for several reasons. One is that we wanted to encourage people to participate. We wanted people to get the sense that like there's still room for you. You could be the person who makes the greatest physics discovery in the history of humanity. There are still opportunities like that out there. And also because we thought it's important that people understand that science doesn't know everything, that it's a process, right? It's not just a list of facts, it's a way of learning about the universe. And so we wrote this book, and the book, you can see, it's about this topic of what out there is in the universe we know and what out there in the universe we don't know. And it's written in a sort of accessible way, but most importantly, it includes a lot of these cartoons by Jorge that I think play a vital role in helping the reader feel comfortable. You pick up a book by an important scientist, and often there's a lot of words in there that the layperson doesn't actually understand. And instead of learning something about the universe, they just get the feeling of being in the presence of a great scientist. But we didn't want that. We wanted the reader not just to have fun along the way, but also to feel comfortable. And there's something about comics, about cartoons, that are not intimidating, right? A cartoon, even as opposed to a figure, a cartoon feels unpretentious. It doesn't feel intimidating. It feels like, hey, you're just reading cartoons, right? And if you're learning physics along the way, great. So for example, we wanted to talk about how mankind had been trying to understand one basic question about the universe, meaning what is the universe made out of, for basically ever, since people have been asking questions, since people have been wondering about the universe. So here's Jorge's depiction of early physicists smashing rocks together to try to understand what they're made out of. But at the core, there is a real concept here. This is not just a joke, right? The origin of the question, what is the universe made out of, comes literally out of smashing stuff together and trying to see how can you make it smaller. And if you make it smaller, can you then smash that stuff together? Can you then smash that stuff together? That's literally what we're doing still at the Large Hadron Collider, is basically smashing little bits of rock together. And so Jorge has this great genius for not just making jokes, but also capturing the essence of the actual science and communicating it through these cartoons. You know, one mystery of particle physics is that it's even possible, and that it's possible to take everything around us apart and understand it in terms of a few basic building blocks. You know, whether it's the periodic table of the elements or even the more fundamental particles, it seems like everything in the world around us is built out of a few basic building blocks. And so, you know, here's Jorge's joke cartoon, which again is funny, thinking about the universe made out of Legos, but there's also a deep concept here. And it's interesting that the universe is this way, that the universe basically follows the Lego philosophy, right? That everything that you see around you is made out of complicated arrangements of simple objects, right? It could have been different. It could have been that the universe was made out of a long list of complex small objects, right? But instead, the complexity doesn't come from the nature of the things you're being built out of. Everything's built out of the same basic stuff. The complexity of the universe, the richness, the beauty, the craziness of the universe comes from the arrangement of those things, just like with Legos, right? With a box of Legos of standard shapes, you can make anything you want. And so that's really amazing. I love the way he captured that in this cartoon. And we also have in the book sort of figures, you know, things that describe the structure of the nature of matter. Here are the fundamental particles, right? We zoom out from the periodic table of elements that everybody's familiar with, and we show that the structure of that periodic table are a set of clues that lead you to understand what's deeper, what lies beneath, peel back, as Dennis Overby would say, another layer of reality. And we do that by showing an analogy, the current periodic table, where we list the fundamental particles that make up everything, the up quark and the down quark and the electron that make up most of matter, and then these other weird particles that exist only in special circumstances. So we have this sort of generic table, but we also, you know, have fun with it. So here, for example, are how all the particles talk to each other. You know, some of these particles can interact with some other particles, some of them can't interact with some other particles. And so in trying to communicate this, you know, Jorge again makes a joke, right? This is like, these relationships are more complicated than a Mexican telenovela. So if you can follow the plot of a soap opera, you can definitely understand particle physics. Again, it's a way to make a joke, but also put you at ease, to make you feel like, hey, this isn't anything you can't understand. I think for too long, physics has sort of lived off the idea that this is something only geniuses could ever do, but instead it's the opposite, right? Physics belongs to everyone. Physics questions like the nature of the universe and the structure of matter and the origin of everything are questions everybody wants to know the answers to and deserves to understand the current state of research. And so that's another reason why we wrote this book. And so here, for example, is Jorge's description of antimatter, right? You have quarks inside a proton and anti-quarks inside an antiproton. And so, of course, we thought about, you know, what would be the anti-version of our book? Be written by somebody who actually does understand the universe. And the book is not just about particle physics. The book also is about the rest of the universe, trying to understand what is the nature of matter, because, you know, we have spent a long time trying to understand the matter that we are made out of and the matter that we see around us and the matter in galaxies and stars and hamsters. But it turns out that most of the universe is something else. And so sometimes our cartoons are a little bit more like figures, right? But in a way that makes a point. And so here, for example, here's a cartoon. Here's a figure that makes a point about the nature of matter and how much we understand about the universe, right? That most of the universe, dark energy and dark matter, are things we have yet to understand. The biggest slices of the pie of the universe are things that we've only begun as scientists to really grapple with in earnest. And that what we have understood so far is basically everything that science has accomplished so far is basically 5%, which can be dismissed as just bad puns. And we try to use Jorge's cartooning skill and ability to draw, to draw and to illustrate it, to make sort of understanding of these tricky concepts, these concepts that are hard to grapple with, a little bit easier. For example, something that we try to tackle in the book that I think is especially difficult for people to really digest is the question of the nature of space itself, right? What is space? think most people out there, if you ask them this question, they would think that space is just sort of like the backdrop to the universe. It's like the stage on which things happen. It's not a thing in itself, it's just sort of like the background. And maybe even it's abstract, it's like defined by humanity. But instead, as you probably know, space is something much more interesting and complex. Einstein shows us that space can do things, right? It has a nature, it has a topology, and it has a scale. It can expand, right? That's what dark energy is doing. It can bend, right? That's what happens when space is in the presence of a concentration of mass, that it changes the curvature of space itself. It can even ripple, right? That's gravitational waves. And so in this one, Jorge has added one crazy bonkers idea, cartwheels. And here we really had to walk a fine line. We want to communicate the goofiness of what space actually can do by tossing in a joke idea, but we never want to confuse people that the jokes are actual science. And sometimes the science itself is so crazy, you have to really think carefully about whether or not your joke's going to be misinterpreted. Somebody out there might actually think space can do cartwheels. I mean, it's already silly that space can bend and ripple and expand. We also try to tackle the concept of what is time, and thinking about time as a bunch of slices of the status of the universe. And so Jorge has these drawings to help us visualize, help us create a common mental image. And I think a key thing when you're writing is to try to paint a picture in somebody's mind of how something works. And what's better than painting a picture than actually just drawing the picture, the idea you have in your mind. And here, for example, is another very tricky concept, the idea of additional dimensions of space and time. You know, if our universe is not just three-dimensional space, but instead is embedded in a larger, higher dimensional space, where would those dimensions, where could they be? And so sometimes people talk about these dimensions as being curled up rather than being infinite spatial dimensions. They are looped up. And so here Jorge tries to explain that topic and throws in a joke about a famous performer. And then, you know, sometimes we just make jokes just to sort of alleviate the drama or alleviate the sort of cognitive burden. Sometimes when you're learning about physics, you just sort of need a break. And so instead of needing the reader to put the book down and walk away to get a break, we give them breaks just by inserting a few jokes here and there. Sometimes the charts themselves have a joke in it here or there about the chart, right? So we have a fun series of charts that make fun of themselves. But in general, we try to convey in our book this idea that we are still clueless, that we don't understand the universe. And so as a researcher, I was curious, how well did the book work? Like, you know, it sold a good number of copies, that's great. But the goal of the book was not to make money. The goal of the book was to teach people about science, to help them understand that they could understand as much as scientists do. So I went and I read, I probably made a mistake, and I read the Amazon reviews of our book, which are hilarious and entertaining. Here's one of my favorites. It says that this book is laced with nonsense, but it's profound nonsense. There's little in this book I didn't already know, but now I know it better. And so this reader especially enjoyed the humility, and I feel like it's the comics that really deliver that, the sense that we're not pretentious folks in an ivory tower, we're just people doodling on paper and trying to understand the universe. And then of course you have folks out there who think we misunderstood the universe because they have a theory of everything and they have understood the universe. This person, for example, gave us 2 out of 5 stars because we ignored their personal research on gravitational theory. This person actually did send me his theory of the universe, which we decided not to include in the book or in a follow-up. Here's, for example, somebody who didn't enjoy the book. He says, I know more than these guys and I don't know all that much, which is fine. Here's, for example, somebody who very disappointed in the book, gave us 1 star on Amazon, which is very difficult for an author. But their main issue was that the book was left on the doorstop in the pouring rain and therefore ruined. All right, so today I've tried to tell you about my journey as a physicist and as an educator trying to figure out how to communicate the crazy topics of science to students in the classroom and also to folks out there who want to understand the universe, who want a road into these complex and fascinating topics that I think really do belong to everybody, and also to folks out there who need to know a little bit of physics and maybe aren't aware of how important it is. So my lesson is that, so what I've learned in my experience is that it's very important to speak the language of your audience, to know how they can learn what they are thinking so that your ideas slot into their brain, and to use cartoons and visual aids to disarm them and to communicate. Thanks very much for all of your attention.
Thanks, Daniel. So we have a couple of questions. Magdalena, would you like to read the?
Yeah, absolutely. I can start, but Danielle, that was a fantastic talk, and I think I took notes all the time, and I just loved what you said, and so much of it resonated with me. And I just really like the way you said that physics belongs to everyone, and we just need to learn to speak the language of our audiences. So that was great. I'll start with the first question, and then Matteo, you can take the next. So Julia wants to know, do you have any data on whether your target audience understands the comics the way you intend?
Yeah, great question. I do not. And
you have no idea.
I have no idea, but I love that question because that's the right question to ask: is this working? A lot of educational efforts are done by instinct or intuition, and we don't know whether it works or not. And I think that the right question, the right way to approach it is to try something and then to test it and then to measure it. So no, and I'm not an educational researcher, so I wouldn't even necessarily know how to set up that study. But if somebody wanted to do a study like that, I would be very interested in the outcome and very gratified to know how to modify future efforts in order to make them more effective. I do get informal responses from folks who read the book and tell me, but that's definitely, there's a selection effect there. People tend to write me more often when they like the book, when they've enjoyed the comics, and they say, thank you, the comics helped me understand. People who found the comics annoying or confusing, more likely to just stop reading the book and move on with their lives. So no, I don't have the answer to that question, but I would love to. Thank you very much for asking it.
Well, we have another question from an anonymous. There is a lead female character in the. Sorry, one moment. So, the question is about the fact that the role of diversity in physics. What can be done to transmit the importance of diversity in your book or podcast?
Great question. Thank you very much for bringing that up. I completely agree that there is a problem with diversity and inclusion in academic physics. And one thing that we try to do in our book and podcast is to highlight the role of underrepresented folks in physics. So for example, in the book, we have cartoons where you have a scientist doing something, and we try to, as often, make that scientist a woman, or make it a person of color, or give them a different appearance than this sort of generic stereotype image of a scientist. I think that helps folks reading it to see themselves in the pages. And in terms of the podcast, we often have a chance to interview experts. We will talk about the Mars landing, and we want to talk to somebody who's actually on the team. So we work hard to find female voices there, for example, or voices of people of color, because for the same reason, we want folks out there to hear somebody like them being part of this. We want them to know that everybody can be anywhere, and that these things could be open to everybody. And in our television show, the lead characters are women and little girls. And that's important to us because we think that hasn't been represented enough on television. So we can make little efforts, but we can't solve the whole problem.
Thank you, Daniel. So I see that Valentina asks, first of all, she says, thank you, very great talk and great book. Do you also talk about modified gravity in your book?
We haven't talked about modified gravity in detail in the book, but we did actually dig into it in a podcast episode. It's really a fascinating topic. And I think especially it shows not just, how a really interesting and important science topic is being addressed from a scientific point of view, but also sociologically. There are competing groups inside science. How do they resolve a conflict between themselves without it being acrimonious and personal? How does science make progress? I think it's really healthy to have several different competing ideas. Even if one seems sort of dominant, it's very valuable to maintain other islands of ideas and build those up, because you never know what that's going to lead to. It might not solve this problem, it might solve something else. And so I think it's important not to be dismissive of those ideas. Personally, I don't think MOND is a description of the universe, but it's important to show people why you think that way and what the evidence is and what tests you could do to distinguish between one and the other. So if you're really interested in that, we have a whole podcast episode about it. I encourage you to listen and to write in if you have other questions about it.
Great, thank you, Daniel.
Okay, and it seems to me that there are other questions also in the chat room. So there is.
So maybe while people, I'm keen to ask a question actually. So I'll leave our audience another minute or two to think about more questions. So Daniel, you have so much experience when it comes to translating scientific ideas to different audiences. But as a physicist and scientist yourself, you also have to think about scientific ideas from different perspectives. Have you learned something new and profound about physics or science or the world by trying to explain scientific ideas to different audiences?
I really have. In writing these things, I needed to think about them in a different way. And frankly, I needed to grapple with them in a level that's sort of deeper. The hardest questions are the simplest ones to understand. And in the process of writing the book, I realized that we were jumping over some of the really interesting questions. Like, I was excited to talk about special relativity and time dilation. And in explaining this to Jorge and talking about how to present it in the book, he just backed me up and he was like, hold on a second, what is this we're talking about? What is space anyway? And then I realized that, that's a hard question. I'm not even sure I know the answer. And so in the process of writing this book, we often just had to back up and back up and back up and realize that there are basic concepts that as physicists, we don't think about that much, which really deserve, a deep dive. Another example is mass. What is mass in E equals mc squared? It's a complicated concept. There's inertial mass and there's gravitational mass and internal mass, and it's tricky. And teasing these things out, in order to explain them clearly, you have to have a really deep and clear understanding. And I realized I didn't always, so I needed to dive into those topics. And then in our podcast, we cover a lot of really broad topics, from particle physics and cosmology to quantum mechanics. And so it's given me, frankly, an opportunity, an excuse to think clearly and carefully about these topics that otherwise, as a particle physicist in my little sub field, I wouldn't necessarily give myself 2 hours in a day to say, what is a quantum dot? How does it work? What does it really mean? What are the interesting, hard questions about it? So I think it's really broadened my knowledge of physics. I know more about many other topics in physics I otherwise wouldn't have dug into, because I've tried to understand them well enough to explain them to my kids or to the general public. So it's been a lot of fun.
Okay, so we have other questions from Jep. Well, modern physics is far away from everyday life. Do you have suggestions for more everyday life topics we could introduce to students?
Modern physics is far away from everyday life. This is true. Not many people get to ride on spaceships or orbit black holes. That's certainly true. And there is a lot of, really interesting physics in the everyday, a lot of topics that are fascinating. For example, there's a question of how do microwave ovens work? There's a lot of really interesting physics in how your microwave works, and a lot of people don't understand it. Or, you go to the doctor and they use an MRI. how does that work? How are they taking a picture of the inside of your body? I think also a really interesting angle is not just like, how does it work, but how was it discovered? Something that's really interesting to me is how we went from a world where we didn't understand something or didn't know something, and then we did. So on the line of medical applications, like just think about the discovery of X-rays. There was a time when we didn't know the universe was filled with invisible penetrating radiation that could tell us amazing things about the insides of our body and the insides of, the pyramids, and now we do. And I think that moment of discovery is fascinating, and it really shows people not just how physics works, but how we can make progress, how you could be the person to discover something breathtaking about the universe, something that shows you the universe is different from the way you imagined it might be. So I think showing them those moments of discovery, which don't always happen in crazy physics laboratories, is another way to give people a handle for what physics is doing to help us understand the universe and how that happens. Another really, and one more that's really fascinating and sort of surprising that I dug into recently is how a bicycle works. It turns out that the physics of a bicycle, which a lot of people think is simple, like, oh, it's just gyroscopes on the wheels, that's actually totally wrong. And we don't actually even really know why bicycles balance. And there's a whole crazy community of folks out there building weird bicycles with different size wheels and arrangements to try to understand why bicycles balance. So there's a lot of deep physics mysteries still in the things that you experience every day.
Okay, great. Jens has a question. He says, when I give seminars to young scientists about communicating their research, a very common question is how these communication efforts are rewarded from the institutes. What is your experience on the reactions of colleagues or in your pre-professor time supervisors when you invest a significant amount of time into communication?
Great question, and a very tricky one. It's true that scientists tend to be sometimes judgmental. I've had a variety. So first of all, I didn't do significant science communication until I was already a professor. And that's because I needed to spend all of my time doing research. It's such a competitive job market that you essentially needed to be 100% research animal to get the job. But once I did, then I branched out to these other interests. And I've had sort of two different kinds of reactions. People in my department at UC Irvine, very supportive. They're there because they love physics and they want people to understand and appreciate physics. And so they love it and they love the book and they want to encourage me. And the university itself, has been very positive about it. Inside the particle physics community, while people in general are positive, there is this sense that you can't do everything. And so I think people see this work I'm doing for outreach and they ask themselves, is Daniel still doing research? Can you be a scientist on the cutting edge and also do this kind of stuff? My research hasn't stopped. I'm still putting out the same number of papers and doing research. I have a team of 8 grad students and a few postdocs, and I'm still doing it. But I think, to be honest, probably it has damaged my reputation inside the hardcore research community somewhat, but it's a balance. You have to decide where to put your energy. You can't do every research topic. You can't do everything. And I've decided this is important to me and it's fun. And to me, the best career advice I ever got was do the things where you find joy, because those are the things you're going to do well. That's where you're going to let your creativity flourish. And so that's what I'm doing. But it's a difficult choice for everybody.
Yeah. Yes, I totally agree. There is another question, perhaps it's very similar to the Julia's one. I'm curious about the age of people more interested in this format.
Yeah, great question. We were curious about that also. And we get emails from folks down to about 7 years old who read the book and are interested in it. And our podcast listeners ages, it's like 9 to 99. So we didn't intend to be like a young adult version of popular science, but I think that there is an accessibility there. There's a native sort of content that people are familiar with this type of information. We were a little worried about turning off people who were like in their 40s and wanted to read a book about science and picked it up and saw comics in it. But it's not for everybody. You have to pick your audience. I think that there are a lot of really interesting, deep things about physics in the book, and the comics are there to make you feel comfortable and entertained. If you just want to feel like you're in the presence of a great scientist, then there's lots of other books out there as well. Sean Carroll does a great job of explaining science.
Okay. Another question, and I think it's an important one, is there a more interactive way to use comics, not only to put audience to read them in silence? If there is something you have in mind. Magnificent presentation, thank you. That was from Dell, yeah.
Thanks very much. Our television show is a little bit more interactive because there's voices and there's actors, but together with the television show, we also got a grant to produce two different things. One are digital games. So these are games that kids at home, they're designed for 3 to 6 year olds. They can sit at home and they can play little games where they have to do science. So for example, one game is they take the character from the TV show and they have to dress it up in clothing or in costumes so that she can play hide and seek with her friends and more effectively hide because she's camouflaged. So she can do a little bit of science. Another is a really fascinating research topic that we're working on using artificial intelligence and natural language processing. A lot of television shows the character breaks a fourth wall, like maybe you see Dora the Explorer, where you're watching a television show and then Dora asks the camera, "What do you think?" And in studies, this is where I've actually read some of the educational literature, kids shout out answers to the screen, but often it's wrong. And of course, Dora can't hear them and she goes, "That's right." And that actually enforces and enhances misunderstandings. So we have a project where it runs on a tablet so it can actually use the microphone, and the TV show pauses and the character asks you, "What do you think about this question?" And it can hear the kid's response, digest it, and respond with appropriate context, like, or try thinking about it this way, or that actually is correct. So this is an AI-powered natural language processing, animated, interactive educational experience. And the research shows that kids who use this rather than just watching an episode learn the science better, and especially for English language learners, kids who don't have English in the home, but are learning English in school. It's much more helpful for them to grasp the science. And one of the missions of PBS and of our television show is to bring these science questions, not just to folks whose parents already take them on nature walks every weekend, but people who live in the city or who don't necessarily have those same opportunities. And so I think these interactive kind of experiences can really help there. Great question, thank you very much.
Yeah. Next question about, do you have any feedback? This project has encouraged young people into science. You have any feedback from, perhaps too soon, I don't know.
I hope it has. I just have some anecdotal experience. Folks write in and say that they listen to the podcast or they read the book together with their kids, and it helps them talk to their kids about science and answer their questions. And so that's certainly my goal, is that folks out there who are excited about science feel like it's accessible to them and therefore they could participate. So I don't have any hard evidence, but I've encouraged a lot of folks over email who write to me and are excited about it and want to get into science to give it a try. So I certainly hope so, but I don't have any evidence.
Okay, Daniel, it looks like you have inspired a lot of educational researchers and science educators to actually go and test your comics. So Sean asks, would you encourage teachers to use your cartoon scenarios in the classrooms on a PowerPoint maybe? What would you like to know from students, from how students understand your scenarios? So if there was research being done, what would you like to know?
Yeah, that's a great question. I think a first step is to carefully formulate, the research question. We actually have developed a guide for teachers who want to use the book in the classroom that has some material, some discussion questions, some things that teachers can ask. But I haven't carefully thought about, how I would structure a research study, whether somebody has understood the topic better with or without the comics. Like you might give somebody a chapter with or without the figures, and see if they understand the topic better. You'd have to devise some careful questions to measure their level of understanding, but I think that would be fascinating.
I think this last question for this, for Daniel. Really enjoyed your presentation. Will the TV show be on YouTube? Can such outreach work be done without commercial backers?
So yes, some of the episodes are on YouTube. Also, you can get them from the PBS Kids app on streaming, and you can get them on Amazon as well. Can you do it without commercial backers? We don't have any commercial backers. We're supported by a public broadcasting service in the United States, which is supported by a big grant from the Department of Education, and so we're not like sponsored by hats or cold cut foods or anything, or any toys or anything like that. But it's a function, I think, of government, to support education and to encourage science literacy. And I think it's a very important one.
I agree. Well, Magdalena, what do you think? I think it's enough for the Daniel today, because we had a wonderful presentation. Totally agree with one of the audience.
Thank you very much, everybody.
Thank you, Daniel. Thank you, Dan.
So I think we have 3 minutes of a break before we continue with our next keynote speaker, Ute. So if you want to get some coffee or some drinks, snacks, wherever you are, in whichever time zone you are, you have 3 minutes. And then we're going to start at 6:10 with our next keynote speaker.
A virtual break for a real coffee.
So I hope all of you had, I see Matteo and his coffee, perfect. So we continue with our next keynote speaker, Ute Kraus, and it is my absolute pleasure to have her with us today. Ute is a professor of physics and physics education at the University of Hildesheim in Germany. And Ute is a true pioneer in relativistic visualizations. And she also works on new and interesting approaches to teach special and general relativity at different age levels, from secondary school students to undergraduate physics students to physics teacher students. And she and her team in Hildesheim maintain the website spacetimetravel.org. And on this website, they host open educational resources that make their research outcomes available for teaching. So I encourage you to check out the spacetimetravel.org after Ute has given her presentation. And now it's up to you, Ute.
Thank you very much. I'm just trying to share my screen. Thank you very much. Thank you very much, Magdalena, for the introduction and also for the invitation to give this talk. General relativity for secondary school. And I would like to start with a question of how much general relativity do we actually have in secondary school? We have been studying curriculum documents for quite a while, as many of you know, and I know that many of those present have contributed to this study. And I'm showing you an overview with some first results. So on this map, you see countries in green, where we definitely found GR mentioned explicitly in the curricula. In yellow, where we found GR mentioned, but not in the national curriculum, rather in some of the state curricula or provincial curricula. And in yellow, where we have seen the data and know that GR is not mentioned. You also see most of the countries are in brown. So there is a lot more scope for more data. And I would be very happy if you can add info for your country or for any country that you're familiar with. We would be happy to hear from you. Now, at the present time, we have found 13 curricula which explicitly mention GR as a required or an optional subject. These are all secondary school curricula for an age group of typically 16 to 18 or 19 years. Some of these have GR as a required topic, some as an optional topic. And we have been looking into the topics, into the contents, into the elements of GR that these curricula prescribe for teaching. So 3 of these 13 curricula are of the type an introduction, or they just mention GR as a keyword, with no further details, but 10 of them have more detailed descriptions. And we have produced this bar graph to show the curricular elements that we have found in these 10 countries listed below. So as you see, the maximum number of mentions is 7, so that there is no single element that is present in all the curricula. So as a first result, we can say that there is no general consensus about what should be part of a first introduction to relativity at school, or general relativity, I should say, at school. We also see that there are some topics more often noted than others. Geometry is one which has many mentions. This is typically the case when curricula say curved spaces or curved space-time or curvature of space-time should be in the should be mentioned, should be addressed. And in one case, we have the keyword non-Euclidean geometry, and in one case only, we have the keyword geodesic. So again, this is not very specific. We also have another peek at astrophysics cosmology. There typically we have mention of black holes, of the expanding universe. In one case, also gravitational waves. Now, I would like to say some words about the topics that we are working on at Hildesheim University. We are focusing on geometry and on phenomena. So what we do is we design models, we design visualizations. We're trying to produce visual aids to show the phenomena and to show the geometry, and to make it possible to work with visualization of geometry to deduce phenomena for certain specific spacetimes. So part of the process is the design, the computation, and part of it is the development of teaching approaches and of units. Units for secondary school and also units for university, for pre-service teacher education, because we think that the education of physics teachers is an important point to enable them to teach this topic. When tests, we do tests by inviting students aged 15 to 19, typically to university, and teaching them the units that we have developed. This is a process of design and evaluation and redesign. And when we find that the unit works for students of different focus, different age groups too, we make these available as open educational resources under spacetimetravel.org, as Magdalena already said. Now in this talk, I should like to give an example for that work. Look at a specific question and show how we try to make this comprehensible by using visual aids, by using visual representations of spaces and spacetimes. There is some previous knowledge that we need for this unit, which is not very much. What we need is that students who work with these models that I'm going to show in a minute, that they are reasonably familiar with Minkowski diagrams. This diagram already shows everything they need to know. A particle at rest has a whirl line which is vertical in the middle of the diagram. A moving particle has an oblique whirl line, and the scaling of the edges is chosen so that a light line so that a light line makes 45 degrees with the axis. And in the following, I'm going to show you how by constructing light lines on a sector model, in this case, students will be able to study our question of exploring the event horizon of a black hole. So what we are going to look at is spaceships, probes, and light signals. And we're going to restrict all of this to the radial direction, that is one spatial direction. So we will have a probe that is falling radially into the black hole. We will look at a spaceship that is keeping its distance to the black hole. This means the spaceship has its engines running all the time, accelerating outwards in a way that it just avoids falling in. And these two will then exchange light signals. And by constructing these light signals using models and diagrams, we can study the space-time of the black hole and including the event horizon. Let me go back for a moment. What we need to do to study this space-time is to give a description, and this description shall be in the way of a model, in the kind of a model or a diagram, without going to advanced mathematics. And the models that we use are sector models. These are tools that permit to represent the space-times of different scenarios. We have done models for black holes, for neutron stars, for gravitational waves, for the expanding universe. And I want to say a few words about what the sector model idea is in principle. So it all goes back to the idea of triangulation. This is something that we know from computer graphics. In order to show a curved surface, what one does is approximate it by a large number of small flat triangles. This idea has been taken up in GR, in the so-called Reggie calculus, described by Reggie in 1961. And this idea is to describe a curved spacetime by means of small, flat sectors, and these small flat means Minkowski geometry sectors. Now this is a fairly abstract concept. It's a 4D spacetime, and these sectors are 4D spacetime tetrahedra. Now we're using Reggie calculus, but we are boiling it down to something much more concrete and going over to physical models. What we do is we look at subspaces of spacetimes, not the full 4D, but we're looking at 2D subspaces like the equatorial plane of a black hole. We're looking at 3D subspaces like, for example, space inside a neutron star, or we can look at space-time in 2D and 3D. And we describe these by means of small uncurved sectors in the spirit of a triangulation. Now these 2D sectors can be built from paper. The 3D sectors can be 3D printed or also built from paper. So we get physical models that we can handle and that give us an overview and an understanding of the geometric of these spaces or spacetimes. Now this is our intro example. The sphere. So to describe the sphere with a sector model, what we have to do is divide up a part of the sphere into small regions. We have chosen them to be quadrangles because they are easier to handle. And then each of these small pieces of area is replaced by a small plane piece of area, by a small plane trapezium. We can glue all these trapezia together. Then we see that the result is an approximation to the surface of the sphere. And we can also see what we can do to make this approximation better, more precise. We just have to use more and smaller quadrangles to do it. We don't use them in the glued up version, however. In order to do geometry, we use the plane version. We arrange them in the plane. And the important thing is that each point on the sphere is represented by some point in one of these sectors, and that the sectors as a whole cover the part of the sphere that they represent completely. Now we use these sector models to study geometry, and geometry with respect to GR has two main topics that we focus on. One is geodesics and one is curvature. Geodesics, because the theory states that light pulses and free particles follow geodesics in space-time. So to construct world lines, we need to construct geodesics. And curvature, because that's the main ingredient in the field equation and allows us to state the connection between curvature, between geometry of space-time and the distribution of matter. Now, in this example, I will talk about geodesics only and show how the study of geodesics in this particular space-time example, radial ray of a black hole, can produce interesting results. To introduce geodesics, we again use the sphere as an example. And for geodesics, we use the definition of geodesic being a locally straight line. Locally straight, we usually explain this by saying, imagine that an ant is crawling over the sphere, and this ant is following a geodesic if it takes each step in the same direction that it took the last step, if it is never making a bend to the left or to the right. In this case, it is a geodesic. And we can translate this definition of a geodesic onto lines on a sector model. Now, if this ant crawls across a sector, then a locally straight line is just a straight line. And when it comes to the border of a sector and it crawls onto the next, if it keeps the direction constant, then the straight line will just extend over the border into the next sector. So when the surface is given as a sector model, finding a geodesic is very simple. You just draw a straight line, use a ruler. So for the problem that I proposed to talk about in this talk, we are interested in world lines and light lines in space-time. So we have one spatial direction, the radial direction into the black hole, and we have time. So we need to translate all of the above, creating sector models, drawing geodesics from space into space-time. Now, a space-time sector is something that we are really all familiar with, and I would like to start with this example from everyday life. This is a schedule of a German secondary school. And what you see is the schedule subdivides space, that is the school building, into rooms, and it subdivides the school day into time slots. And each lesson is what happens in a certain room in a certain time slot. So each lesson is a space-time sector, and the whole of these sectors make up the school day. There are many different ways of subdividing a surface or a space-time or a space into sectors. And for the black hole example, I should like to use a way which one could use the Q method. And I would like to show what this means using an example in Minkowski space, first before going to the curved space of the black hole example. Now this is the Q, right? These people are just standing there waiting for coffee. We want to have a space-time sector model, a space-time sector model for the space-time of this Q. Now each person in the queue has a certain space for himself or for herself. Take the one with the backpack, for example. Its world line is a vertical line because this person is just standing at rest. And the borders of his space in the queue are the dashed vertical lines in the diagram. So this person owns a certain band of space-time, and he can use his own watch to subdivide this band into time slots. This is the way that we can create some space-time sectors for this queue. Now we can do the same thing for the other people waiting here. For example, the lady with a bag, she gets her space in the queue and subdivides it with her with her watch into space-time sectors. In this way, we can get a sector model for this queue. Now we need one more step before we can translate this into the black hole space-time. We need to look at the queue that is spreading out. Now, the person in the middle is just standing there. World line is a vertical line. And the neighbors to the right and to the left are walking away from her. Now, this means that her space in the queue is growing with time. So her space-time band is opening up and getting bigger. She can still subdivide the space-time band into time slots using her watch. So this idea of using a queue to subdivide space-time into sectors will be used for the black hole space-time. For the black hole space-time, the queue, the so-called queue, will be probes. So we will have probes falling into the black hole one after the other in a very regular kind of way. And this diagram just shows two of these probes. On the right, the probes are shown at an early time, on the left at a later time, and you see the distance between them increases. Now this is clearly due to the tidal forces. The probe, which is closer to the black hole, always feels the larger gravitational attraction and will have the larger acceleration. So these cubes form these probes. They form a line, a queue, and a line for which the space in the queue for each of the probes is growing with time. For one of the cubes, with this band of space-time belonging to these cubes getting wider with time, we get a number of space-time sectors like that. And for the next cube, for the next probe, the same, also for all the following cubes. So we have a number of columns, and each column coming from one of the probes. Now we need to think about how to combine them. And when we combine them, how to combine them becomes clear when we pass from one probe to the neighbor in the outward direction. And we look at the two sectors that are neighbors in this diagram. The outward sector is from an earlier time in the free fall of the probe. And at an earlier time, the space belonging to this probe is smaller. So the space-time sector is narrow. So that is the way that we have to arrange these columns of sectors that are due to the different probes. Now with this method, what we get is a model, and we can say that each event in the space-time of this radial ray is represented by a point in one of these space-time bands, in one of these space-time sectors. And that conversely, the space-time sectors taken together, they cover all of the space-time that there is in this radial ray. Now, given a space-time model, what we want to do is look at signals between probes or between probe and spaceship. So we want to construct the light lines, the geodesics for light. Now, how to do this? Now, this is a light line going inwards. The probe on the right emits light in the inward direction. So in the sector of this probe, which is a Minkowski space sector, the light line is a 45-degree line. When it comes to the border of the sector, it leaves this sector and enters the neighboring sector. And all we have to do is let it enter at the corresponding point on the border. And then in the next sector, in the band of the left probe, this light line will again be a 45-degree line, and we can continue from there. So world lines of light are really the easiest geodesics that we can draw, because their direction is fixed, always being 45-degree lines. Now with this preparation, we can look at the complete sector model and study some of the signals that a probe and a spaceship can exchange and see what we can learn about the space-time from them. Now this is a model for 6 of these probes that we use for the cube method. The one that we are going to study is the one as the leftmost one. We have the world line of the probe. And I have also added the world line of the spaceship that is keeping its distance to the black hole constant. So these constant distance world line is computed. So at this point, I should say something about the shape of these sectors. What I told you up to now with the Q method, with the analog in Minkowski space, this is a qualitative view so that one can understand that the band of space-time belonging to one of the probes is a band that is opening up wider with time. But this qualitative idea doesn't tell you how fast it is opening up or what the dimensions of the sector should be. So these dimensions must be calculated. And behind the sector model is the Schwarzschild metric, which we have used to explicitly calculate the world lines of the probes, their distances that they measure at certain time steps. If we did the same thing with the same probe method for a different space-time, we would get, for a different metric, we would get different sized sectors and get different results. So this is a model that is to scale, and there's a lot of theory behind it. And what we should think of is that this model sort of represents the metric of this radial ray space-time in a visual way. And it represents this metric in this triangulation idea way. So in the spirit of the triangulation, we are using small flat pieces, in this case, small Minkowski space pieces that taken together give an approximate description of the non-Minkowski space-time close to the black hole. Now I should like to show, so what we want to do is to study light signals, exchange between the probe in free fall and the spaceship that is keeping its distance. And before we do that, I would like to point out some details of this sector model that we're going to use. One is that I've put these dots on the world line of the probe, and these dots mark intervals of proper time, regular intervals of proper time. The same dots are present on the world line of the spaceship, and they mark the same intervals of proper time. Second, the world line of the probe on the left is continued a little bit beyond the last sector in gray. And this little gray line indicates the proper time of the world line of the probe that is remaining until the probe hits the singularity. So this shows you that this sector model goes very close to the singularity of the black hole. In fact, it is a model which covers both a region outside the horizon and a region inside the horizon. And we will see that in a moment. So the first thing that I would like to show is how to, is from the point of view of the probe. So the probe is falling in, and we want the probe to look back to the spaceship and trying to keep the spaceship in view. So we have, I've chosen some events, and these are the events of snapshots where the probe records light that comes from the outside and potentially from the spaceship. So we need to draw light lines that hit the world line of the probe at these red points. These are here. These are just drawn the same way I described above. These are 45-degree lines in all of the sectors, and they are just continued at the border at the respective border points. And you see that all three lines come from all three lines, when we follow them backwards, hit the world line of the spaceship, which means the probe can always see the spaceship all the way down to the singularity. Now we're going to do the other way around. We want the spaceship to track the probe. because the spaceship might be interested to follow the progress of the probe as far as possible, and hopefully to see the probe hit the singularity. So now we need light lines that arrive at the spaceship from the inside, like this one. This is a zoomed in version of the above. This is a light line which moves outside and reaches the spaceship at this certain marked point. And as you see, this light line comes from the probe. So the spaceship can actually see the probe when moving in. And it can see the probe at a point on its world line that it's a little later than the point where the probe where the probe overtook the spaceship. Now we're going to look at, we're going to have the spaceship take many snapshots of the probe at perfectly regular intervals. And since we need really many snapshots for what I want to show you, I'm not going, they don't all fit on the page, and I'm just not going to show them, but I'm just going to tell you that these are taken at regular intervals, and we are looking at the far left end of the light lines of their origin near the probe. So these are the first three light lines, and these are the first three snapshots, and obviously the spaceship can follow the progress of the probe in the direction of the singularity for this amount of time. Now we take three more snapshots taken at regular intervals, and you see the spaceship can see more of the progress of the probe, but you may also notice that these light lines get a bit closer. The next three snapshots, the light lines get a lot closer, and the last three that I want to show, they are very, very close. So what happens is the spaceship can see the probe at all times, but it's more and more difficult to follow the progress of the probe further. So the spaceship can wait, even if the spaceship waits a very long time to the next snapshot, it may see the probe progressing only a very tiny distance along its world line. Now this looks like there should be a limit somewhere, and we can actually find this limit, and we can actually see that it is a limit. That's this light ray. This is a light ray. It is a 45-degree line. And when you compare this line with the world line of the spaceship, then you see in the first column, they are 3 sectors apart. In the second column, spaceship and the limit line are again 3 sectors apart. And in the third and in the fourth. So they don't get any closer, which means that this is a light emitted outwards, which nevertheless never reaches the spaceship hovering out there. You can imagine that every light emitted, before this limit will eventually reach the spaceship, taking more and more time the closer it is emitted to the limit, but light emitted afterwards will not. And this outward light ray, this light line that we have discovered with looking at signals passing between the probe and the spaceship, this light line is what we call the event horizon. This is the limit between light that can pass outside and light that cannot. So conclusions, what can we learn with this exercise? And I should say that in a workshop, what we would do is give students this sector model printed out on paper or as an interactive simulation, and let them construct at least part of these light lines, null geodesics themselves, so that they can work with it and be confident that these are actually the paths of light. What they can do is they can study the space-time without solving any equations, and they can get quantitative results because this model is a quantitative model. What they can do is they can discover the event horizon. Looking at the snapshots that the spaceship takes, there is obviously a limit. And they can very clearly see the nature of this limit. This is a light line. This is a world line of light, which is outward bound. We can do more, which we don't have the time in this talk. We can follow the probe further inside and can construct geodesics closer to the singularity to try to find out what's happening in there. These sector models are a toolkit that we have developed and are continuing to develop. We have a number of papers and we have teaching material that supplements these papers that you can find on spacetimetravel.org. And I should add that this is joint work with Corvinsan, all of this that I've been telling you. Thank you very much.
Great, thank you for this talk, Ute. I think we'll just give our audience a minute to type in their questions. One comment that I already see, Isabel writes, I think it's very important to touch and think. Congratulations for the talk. I think that's true. And maybe while we're just waiting for questions to come in, I have a question as usual. I've seen you develop the sector model approaches, or I have followed your work for a couple of years now. Could you give us an update on where you are with the virtual sector models and how you see the opportunities or the differences in opportunities that hands-on models and the virtual models can give us and students?
Yes, thank you for the question. Yes, what I've shown you are models that we could print out on paper and then use with a pen and ruler, as I described it. But we have always also started to create virtual sector models, which means that this is an interactive application which you can use in the browser, and you can use drag and drop to move the sectors, and you can use the mouse to draw the lines. So we have created some of these models for spatial sector models of surfaces and also of space-times with one spatial and one time dimension. We are starting to create them. Now, what starting is not enough. There are some, there is an application that shows 3D sectors for curved spaces, which is being created at the University in Turin. Actually, this is joint work with Lorenzo Galante and Salvatore Fiumara. And we are going to continue with this. One of us in Hildesheim is going to start looking at sector models for 2 spatial dimensions plus time, like a 2+1. A decomposition, this is the next that we are doing. We have wondered at the beginning what would be the difference for students using a hands-on approach with a physical model or using the virtual sector models, doing it interactively. We have made tests. There were classes. We separated them into 2 groups, and one group did the virtual models and one group did the physical models, so we could compare. We did this for quite a while, but I would say both were good, right? So these were a lot easier. These questions that they worked on were a lot easier than what I showed here. They were mainly spatial sector models with spatial geodesics. And we tested them with quizzes afterwards, and we found in both cases that they got a good understanding in the sense that they could explain in their own words the concept of a geodesic and the concept of gravitational light deflection in the curved space of a black hole. So we couldn't really find a significant difference between the 2, which is a good sign, I think. Our hypothesis at the moment is that maybe maybe the physical models would be better for younger students. So we hope to be able to use them with students maybe age 15, 14. So we're going to test how far we can go. And the interactive simulation might be better for more advanced students who don't really need to have the model in hand. We're going to test that too, but we haven't done so far.
Me too. I have a question, more in general, comment. Well, I think there is a main theme, a central thread between the two talks by Daniel and Jutta, the power of visualization. I mean, one of the problems in teaching relativity and general relativity in particular is that math is difficult. So we avoid to teach general relativity and also special relativity because in general, people are afraid of difficult deriving from mathematics. Well, as we have seen, the space-time diagrams in Minkowski plane are very easy and powerful. So I think that we should start from this approach rather than Lorentz transformation and mathematical complication in order to introduce the physical meaning of relativity that indeed is geometry.
Thank you for the comment. That was what I wanted to mention but forgot. Daniel spoke about visual aids, especially in special relativity, to make complex ideas more clear and visually clear. And I think that's the same idea that we have in this work, that we are not even trying to explain equations and the solution of equations, and not trying to get this down to more elementary mathematics. That's another approach. And I know people who are working on that. But I think since it's geometry, we have this possibility of doing it in a visual way, because geometry is something which is visual, very visual in nature. And I think this can be translated from special relativity to general relativity. And that's what we hope to do with the models of this kind.
Yeah, we have a couple of questions now. So maybe we start, I see Isa's question on top.
Yeah.
Have you worked with other topologies apart from the sphere?
Yes, we have looked at other surfaces, notably the saddle, because we wanted to show both a surface with positive curvature and a surface with negative curvature to compare the two. So we can compare sector models, we can compare geodesics on these two surfaces. And we have also worked with the torus, because that's a nice quiz geometry. When students have worked with the sphere and the saddle, they know both types of curvature. And when we then present them the sector model of the torus, we can test if they are able to work with it to find out what type of surface that is. We have also worked with other physical models, except the black hole. We have a model for a neutron star interior, because that's a high density interior, and curvature should indicate if matter is present or not. So we can compare curvature in the model of the neutron star with the high density and curvature in the model of the black hole, which is vacuum, so that we can see the matter effects when we compare these two spaces, I should say.
Okay, we have another question. What level, what age do you propose this exercise for?
Oh, the one that I showed is a very advanced one. So far, we've been using this with an adult group of amateur astronomers with a special interest, of course, in topics like black holes. I think we will be able to use this with secondary school students at the end of their school time, possibly those who have chosen an advanced physics course. So this is really one of the more difficult, more complex situations that we look at. But the things about the geometry of the sphere, when we just look at non-Euclidean geometry, quite apart from relativity, it is a mathematics question, really, to say that we look not only at Euclidean geometry in school, but also at non-Euclidean geometry for the sphere, for the saddle. And these are things that we have done with students age 15 or 14 even, and also different types of schools. For those who know it, we had classes from Realschule in Germany who did that. These are not the academically oriented students. Those are students who are on a more professionally oriented school, and they could very well work with these models. So we hope to get down to age 14, maybe 13, but it's not for very young students, probably.
Okay, I see we have a raised hand. So Friedrich would like to pose a question, and I think you should be able to speak now.
I wrote the question in the chat box. Well, first I would like to say I liked your talk very much, Ute.
Thank you.
And it was so clear, and in particular that you avoided, there was in no place all these complications you have with the change of reference frames. I think that's one of the greatest obstacles in teaching relativity. Although you mentioned you use a Minkowski diagram, but finally you did not need all the complications. So, but that's my question. My question is much simpler. How many hours of teaching would you recommend to use for teaching relativity? How many hours for special relativity and how many for general relativity? So that's my question.
Since it's a topic that's very fascinating to me, so I should like to say as many as possible. But if you're talking about like minimum hours, so what we are using when we invite classes to the university, we have a 90-minute class about geodesics and light deflection. And I think geodesics is one aspect of geometry that we need to cover. And we have a roughly 90-minute class on curvature and the field equations. And I think curvature is the other main topic that we should cover. And my idea is that with these two 90-minute classes, which probably in school would need a little more time because you also need time to put down the results or maybe to pick up where you left off. So maybe, let's say 6 times 90 minutes would be like a minimum time for introducing key concepts of general relativity for me.
Okay, thank you.
Maybe just one remark. You said I didn't use change of reference frame. That is true. But also I only showed you how to find light lines. Now we could go on and say we want to have a spaceship entering the black hole, and not just in radio free fall, but in another motion. And we would like to track particle motion, either accelerated or not. In that case, we actually would have to use changes in frame of reference, because we would have to join neighboring sectors, and neighboring sectors are sectors in different reference frames. So we would have to Lorentz transform sectors to work with them, which is a lot more complicated, I think. And I think that's probably university level to do that.
Okay. Well, is the probe and spaceship model available online?
Not yet. If anybody is interested to work with that, to try it out with a group or a class, then you email me. We can send you something.
That's great that you say this, because this question came from Sean, one of the PhD students in Perth of the Einstein First team. And I just have to acknowledge, Sean, it's amazing that you're still with us. It's 2 a.m. in Perth. So quite impressive to see you still awake. Another question by Fadel. Have you implemented this unit with pre-service teachers also?
Yes. We are teaching pre-service teachers at Hildesheim University, and we do have a relativity class, both special and general. And we are using this material that we develop ourselves in these classes, which is also a kind of test for us and is a chance for the students to get some insight into this topic, which they would otherwise, I mean, we couldn't have a standard general relativity class wouldn't fit into the curriculum at all. So yes, we do use it.
Okay. Well, Arun Kumar said that it was a lovely talk, and asks, according to your experience, can the average student at secondary school understand this work?
I think I just so we have these introductory units where we are talking about space only, not space time. And there our experience is that yes, the average student can understand it because we are working with average students. That's an important point, right? We are not inviting especially interested students. We're not inviting classes from special science-oriented schools at all. We just invite complete classes from regular, normal schools of type Gymnasium or Realschule. And they understand these basic units very well. With space-time, I think it's quite a bit more difficult. This is probably something for upper secondary school and maybe something for students who choose advanced physics. But in these cases, I think that yes. I mean, a typical German curriculum would have Minkowski diagrams up to the point where I showed it, just to draw word lines and interpret word lines. And from there, the step to the grooved space-time, it would have to be made more step by step than in this talk, more slowly, with more exercises in between. But I think we can very well do that with an average physics class in grade 11 or 10. I would expect that, yes.
I think it looks like this was all. Isa has just another comment and said it was very interesting. I agree. Thank you so much, Ute.
Thank you.
Now it is time for another break, and then we will be back at 10 past 7 in our Central European time zone, or 10 past wherever you are in your time zone. And we will use the last part of our session to let some of our conference participants introduce themselves and discuss your questions and comments on the presentations and videos that have been uploaded. So see you in a couple of minutes.
Okay, I think we can start in the second, last part of this session. As Magdalena said before, we will give time to the other panelists to introduce their research results. Before doing that, I will ask Lorenzo Iorio, that is our editor-in-chief of Universe. Lorenzo, if you want to add something to our discussion before asking the other participants to present their results.
You wanted to make me a question?
No, just a general comment about the development of the session.
No, it's going rather smooth, and it is interesting. Perhaps I could have asked Ute a point about the use of the Minkowski diagrams. Maybe I've missed something, but a point which should be clarified, especially when one teaches special relativity at some level, is that when we use Minkowski diagrams, we necessarily use Euclidean surfaces. The sheet of paper is an Euclidean surfaces. So we draw figures, pictures, straight lines, and so on, which illustrates non-Euclidean features. So some misunderstanding may arise if this point is not clearly elucidated. I mean, we necessarily make Euclidean drawings, but they refer to pseudo-Euclidean features. This maybe should be an important point, and attention should be paid to this aspect.
Okay, Lorenzo, thank you. Ute, can you answer, or if you want to answer later, we collect other. I don't know if
you would like me to answer.
Yeah.
Now?
Okay, perfect. Yeah.
You're perfectly correct. And I think the best way to explain would be by reference to the sphere again, because that's an example which is very clear. The sphere is curved and the sectors that make up the model are not. But gluing them together, we see that the sectors as a set approximate the sphere. And even not gluing them together, we can have different ways of clarifying that the geometry of the set of sectors approximates the geometry of the sphere, although each of the sectors is Euclidean. I don't know if that's, I think it should, when looking at a sector model, that is something which I didn't do for lack of time. You could always, you should always clarify what type of surface, what type of geometry that is. So for the space-time sector model, we could have tested for curvature, for example. It could be just a strange way of dividing up a Minkowski space, and it could be a space of no curvature, or we could test and find, no, this is a space with curvature, it is not Minkowski space.
Yes, but even before talking about curvature, even at the level of Minkowski space-time, pupils should be elucidated about this fact that we use necessarily Euclidean pictures and drawings for explaining pseudo-Euclidean relations. This was I mean, the problem arises probably even at the Minkowskian level before
yes, I agree.
at a more advanced level when curvature enters the game.
Yeah. I agree. The Minkowski diagram represents a space-time, but it is drawn on a piece of paper, which is space.
Yeah.
And there's a difference there.
Thank you, Lorenzo. Well, we are going to proceed in alphabetical order, so let me list the names. We'll start with Andrea, then Caterina. Costantino is not here, so we jump to Cristina, then Lorenzo, Paul, and eventually Sarah. So the idea is to give you 3-4 minutes to present shortly the main result that you have already uploaded on the website. And then we have time to short discussion at the end. So Andrea, if you want, you can start.
Hello, everyone. My name is Andrea Lopez. I am a PhD student at the University of Innsbruck. And I'm going to present, can I share my screen? I'm going to present to you this work together with Andreas Hartmann and Wolfgang Thur that is called Encrypt Me, and you can find it here already. And in this work, we have an innovative approach to the study of quantum mechanics, and in particular, we consider how to develop the qubit and also more advanced concepts like entanglement and bell tests and quantum cryptography. And in particular, we do it in an embodied experience where the students play the role of both the scientists and the qubits. So there is a game that can be played in any type of context, either in high school environments or undergraduate or any other science festivals, for example, where they can, without the need of expensive laboratories, they can obtain the same results as if they were in a real laboratory, with the students playing the role of qubits. And in particular, in this job, we extend a little bit one previous work that we have called Entangle Me, in order to incorporate bell tests and quantum cryptography. We have in here we have this this notion where the students orientate their body to the direction of the block vector in order to represent a qubit. And in particular, what we also do is that the scientist plays the game of measuring the qubit by throwing a ball at the qubit student. So, for example, if the scientist wants to measure this this qubit student will throw a ball, and then the student should orientate their body towards the direction that the scientist chose in order to collapse to the given state. And then it will communicate the outcome to the scientist. And with this simple approach, we can also incorporate entanglement by having, in particular, pairs of students that will play this entanglement pair that rotate around this block plane that we paint on the floor until one of the qubits is measured, and then they should stop and then move towards the measurement direction that the scientist chose. And then when the second scientist measures the second qubit, then they will get correlated results because they are holding hands, as you see here in the picture. And with this, we can also repeat, make this repetition of the measurements in order to test bell tests, which are a very advanced concept in quantum mechanics. But with this approach, we make it accessible to the general public and also to high school students that can repeat this process of measuring and can obtain this CHH inequality to test for this local realism. And in addition, we can also play other things like quantum crypto, where we only need two scientists, one that prepares the states and the other one that measures, in order to create this scheme. So yeah, if you have any questions, please go ahead.
Perhaps we could collect the questions at the end, so we will have time to discuss. Then now, Caterina, you can start whenever you want.
Yes, hello. I would like to ask you if it's possible that I share the screen. I try. Okay. So
if it works, yeah.
Yeah, exactly. I thought the same. Okay, so meanwhile, I introduce myself. I'm Caterina Foti. I'm a postdoc physicist at Aalto University in Finland, in the group of Professor Sabrina Maniscalco, who is a professor of quantum information and technologies at University of Helsinki and Aalto University. And together we developed with the two of us and other people, we developed a platform that I would like to show you. Okay, so this is an online platform containing multimedia resources with the aim of teaching quantum science and technologies to anyone, and regardless of their age and background. And most importantly, it's this in a playful way, without giving away scientific correctness, of course. So our main idea behind this platform is that people learn in different ways, and following and inspired by the idea of our garden of multiple intelligences, we tried to develop this platform where people can learn through different learning approaches. And to make clearer what I'm saying, I will show you our first content, that is Quest. It's our quantum dictionary, where you can find a list. For the moment, they are only 10, but we are planning of expanding it in the future. So here you can find fundamental key concepts about quantum physics and science. You can read which entries we have already developed. And for each of these entries, we try to illustrate a concept, for example, entanglement, following different approaches. So we have different sections: play, discover, learn, and apply, the most recent one. In the play section, we use video games to engage people and to build an intuition. In the discover, so for example, here, okay, you can see here, there is this Quantum Solitaire, which is a game developed by James Button. By the way, we didn't develop all the video games that we collected in the platform. They were developed by different people in different countries. We selected them looking around on the web, and then we collected what we thought were the best on the platform. So this is the play part. Then you have the discover part, where you find two different kind of contents. So some videos, in particular in each entries, I'll start from the second video. You will find a short video where we asked to an expert of the field, so to a quantum physicist, to introduce the concept to his or her grandma. In the case of entanglement, we had a very special guest who was Professor Monkey. I invite you to discover who is behind Professor Monkey. But yes, the main message here is that in this video, an expert of the field tried to explain the concept in very simple terms. And then we are currently developing what we call the quantum pills. Quantum pills are animations that we developed together with VIS, which is a startup devoted to outreach, science outreach based in Pisa, Italy. And for the moment, we have only 2 quantum pills. One is about entanglement, this one. The other one is about quantum science, quantum physics in general, but we are planning to add all the other in the future. In the discover part, then there is an explanation of the concept starting from a physical experiment. In particular, here we use the Stern and Gerlach one. And here we try to introduce the physical concept without digging into the mathematical formalism. And then thirdly, there is the learn part where the formalism is introduced. So here is let's say, the traditional mathematical logic approach that usually is used to teach quantum physics. And then a new section that we're developing in partnership with Strangeworks is apply, where people can find simple code samples in order to apply what they learned working and coding on real quantum devices. So yeah, I hope that I give you
perfect. You are perfect in
introduction.
Time. Yes, okay. Very interesting introduction.
And yeah, and please, we are really eager to collaborate with the people interested in quantum physics and technologies. So I hope to be in touch with you.
Well, I think it's a good opportunity to make connections. So
yeah.
Okay, I see Costantino is eventually here. So Costantino, you can, if you want, you can share your screen and present your result. Well, we have 4 or 5 minutes in order to have a nice discussion at the end.
I try to do that. I don't know if you see my screen. It is very messy, but I start from the end. The few images that I prepared today with a small video.
This is our soccer field.
This is the video in the soccer field of our school, and I have had the idea to create a meridian line. In the video, I already presented in this Congress the original meridian line of Santa Maria degli Angeli, made in 1702, is used to measure the position, the apparent position of the sun up to a precision of an arc second. And here is a way to realize the same, not the same, but a similar objective with a daily situation, a soccer field, a shadow, and the other thing necessary to do this is a very precise clock. So in this case, we have a gnomon 10 meters 8, so a length of the meridian line around 20 meters. If we are able to measure the things with a precision of 1 millimeter, you know the relative error what is. So this is the application of what I presented in the video for this Congress. I want to show some other video that I made 3 days ago in the Basilica. This is the entrance of the sun in the sign of Pisces. And you see really this thing in 2 dimensions on the marble of 1700. How much we can be precise in know this phenomenon. Entrance in a zodiacal sign is nothing magic thing, but is a geometrical concept of 1/12 of the orbit of the Earth. So always timing, precise timing is necessary to know this phenomenon. And the other is the traditional meridian timing. So the camera is fixed and the image of the sun, now I put it in the real velocity, you see the turbulence of atmosphere giving an uncertainty up to 0.3 second of time, which correspond to some arc seconds in angular position, but this is the first contact, and during the rest of my talk you will see all the phenomenon of the meridian transit. In this case you have 135 is the tangent of the zenithal angle multiplied by 100. So the zenithal angle in this case, in this position, is 53. Here is 53.5. And if you do the tangent of this number, you obtain 1.35. But the position, this one and the opposite one, is possible to be measured up to 1 millimeter of accuracy. 1 millimeter in meridian transit over 50 meters corresponds to 4 arc seconds. If you know the position of the sun up to this dimension, you can recover the quality of the orbit of the Earth in a circular motion model. But also, if you know the same about the position of the stars observed with this kind of instrument, you can find stellar aberration. The amplitude of stellar aberration that you know is the first relativistic effect in positional astronomy. This is possible to be measured with such an instrument. And so my idea is to introduce the students to a very high precision observation with a very simple instrument, because a meridian line is just a right triangle. So all you have to know is the geometry of right triangles. And if you have a splendid instrument like this one, 1702 Basilica of Santa Maria degli Angeli in Rome, made by Francesco Bianchini and paid by the Pope Clemens XI, you can use it. But if you don't have it, you can do it in a soccer field with very simple instrument, adding a watch and using accurate ephemeris. I think I gave an idea of what I think about teaching modern physics. Modern physics without very accurate measurements and very accurate data analysis is not useful, according to me, in even in high school. But unfortunately, the most activities in high school is using textbooks and not real data.
Thank you.
Disposition for everything else.
Thank you, Costantino. I think it's a beautiful mix of art and science and practical activities. So now, Cristina, if you have the possibility of sharing your screen, you can start.
Okay, so yes, this is a project to show particle physics for primary school students. And I will show the basic idea that I had some years ago. And then actually there is an Italian project. They have submitted a paper to this conference. So first of all, why targeting primary schools? So the idea is that, in fact, we would like to increase the science capital of a nation, in the case initially UK, but generally. And also we would like to improve the attitude of children towards science and scientists, because this will be part of what they are as citizens. And in fact, there are studies that show that children develop awareness and attitude towards science and scientists at a very early age. In particular, for example, they can come across the research done at CERN in particle physics, because sometimes that's in the news. The other thing is that despite what people think, that particle physics is very abstract and obscure, actually some concept, for example, particle families, is something that children can understand and relate to their own experience. And so the idea led to the development in co-creation with a charity in UK that is called the Ogden Trust, that takes care of the training of primary school teachers of these workshops. So the idea is having some process of learning through playing, and in particular to relate to particles through these fluffy toys that is called a particle zoo, but then I also made my own, and then use card games to familiarize with the concept of particles, what they are, their characteristics, and how they interact. And then give students the freedom of choice to express themselves, and then put in action what they've learned and communicate to each other to share what they've learned and their experience in general. So the workshop has a particular structure that starts with an introductory talk to put all the students more or less on a similar level to start with, because I've experienced myself that there is a huge difference. Some students know already what quarks are, or at least they've heard about it, and others have no idea about the atoms. So there is a vast difference. And then after the introductory talk, where the basic building blocks of the universe are presented, and so the various particles are shown as an idea and the basic characteristics, then the students start playing with Happy Families card game to learn the particle characteristics. Then they pass to make a little model with just plasticines and balls, but actually the decorations of the balls must be inspired to the particle characteristics, and the students are asked and accounted for how they represent the particle characteristics on this specific model that they're making. And then they share with each other why they exactly did so. Then there is a second step, which is how particles interact. And so there is a snap card game based on likes and dislikes. And so how people, for example, even the same family, like or dislike particularly some members, so particles interact with some others that particularly like, and for example, they will not interact with some other particle that they don't like. And then again, to put in context their creativity and let them express what they've learned and how their own interpret this, we ask them to produce a creative piece of something like creative writing, a show, a sketch, anything that illustrates a particular particle interaction that they want to visualize. So one thing that I really want to stress is that I started with this workshop, and it's clear that from a scientific point of view, one has to come into, I mean, you have to present the concept in a simplified way, obviously, because this is primary school. Nevertheless, there are ideas that I really wanted to put in this workshop. And so, for example, that the matter has building blocks, that we use accelerators to investigate what happens in particle collisions, why we use particle collisions specifically as an instrument of investigation, why we have certain type of detectors in the CERN experiments, and the fact that particles actually are divided in different categories, and each category has its own characteristic and its way to interact. So then the students start making models, and they are indeed quite pretty. And the idea is that they make models and they put plastics in a different way depending on how heavy the particle is, and they also decorate in a way that illustrates some particular characteristic of the particle. There is also, I've come across the fact that students really like the idea of matter and antimatter, which is very close to my own research, so I really wanted to put this in. And so the idea that the matter and antimatter are the same, but with some characteristics that is opposite. And then there is this creative approach to learning that there are some, masterpieces coming from this that I wasn't expecting. And actually, I also wanted to talk about Feynman diagram, which is really quite a complex thing on its own. But as you see in one of the example picture at the bottom, students try to create Feynman diagrams with what is called a sort of bendy things, colored bendy things, and then they basically try to write stories or songs about these interactions. Now we try to evaluate this.
Cristina, just a moment, just if you can jump to the conclusion, because we can have more time for discussion later.
Absolutely. So this is my last page that it was translated in Italian and Greek. And it was used in primary school in Bergamo and Athens. And indeed, the primary school project has been submitted as a paper to this conference.
Thank you, Cristina. Now, Lorenzo Galante.
My name is Lorenzo Galante. I work at Politecnico di Torino. I'm going to spend a few words about the learning environment I've built for the teaching and learning of relativistic dynamics at secondary school level. We can look at this educational environment as a playground where a teacher can bring his students to play, which means to explore, inquire, and become familiar with basic aspects of relativistic dynamics. As in every playground, also in this educational environment, we have some play structures, playing facilities that can let people play. In particular, in this learning environment designed for the teaching of relativistic dynamics, we have two preliminary and training and playing tools, which are two interactive applications that you can see here displayed in my screen, that are used to introduce the basic concept of relativistic dynamics. And then at the end, you have a third interactive environment that I will show you later, in which students can play a real role-play game mastered by their teacher. So let's start talking about the first training tools of this learning environment, which are two interactive applications, the two that you can see here, in which the students can basically explore and become familiar with the energy, the Einstein energy relation, connecting energy, mass, and momentum of a system, with a special focus on the energy relation of a system composed by one single particle and of a system composed by two particles. So we're playing with these two training tools. Students have the opportunity to have an immediate and clear and geometrical visualization of the Einstein relations, and to learn and become familiar with the new that the Einstein theory gave and put into the inserted into modern physics. Once these training activities are carried out are completed by the students, they have the required knowledge in order to play the role play game with their teacher. And here comes the third interactive environment, which is this one, in which the find the mystery which is hidden behind the collision among particles that you can see portrayed inside the this interactive application. They have to find the mystery, and then once they have discovered the mystery, which is hidden behind this interaction, they have to try to find solution and propose solution, discussing with their teammates to try to solve the problem they have discovered. With this application, they can start in measuring the momentum of the particles involved. They can use circles. They can fit the tracks. They can find the radius of curvature of each track, and they have to calculate by their own the momentum of each particle. And once they have done this, they can ask the application to show the vectors representing the momenta by clicking, for example, in these boxes. And so they can discover that in this particular collision event, the momentum is not conserved, and this is what they have to try to explain. And the interesting part of this role play game is that they are asked to think and to play the role of particle physicists. They are to do the things that usually particle physicists do in order to analyze collision events, and they have to use things they study at school, and in particular they have to put immediately into action what they have learned with the training preliminary stage using the previous tools I've showed to you, and in particular the concept of mass of a system composed by more than one particle. So what are the outcomes that we expect from this kind of activities?
So if you can jump to the conclusion.
There are two main aspects that I want to highlight. Yes, I'm concluding. Yeah. The first one is that along this educational progress, we stimulate the student to be active and to participate actively to the learning process. And the second one, which is very important, is that the students, we are asking the student to perform, to carry out an identification process with what they are studying, because we are asking them to think and to play the role of a particle physicist. And this, we believe, is a very important aspect that can increase and stimulate the possibility for the students to use this critical thinking and to reach a better understanding of what he is studying. Thank you very much for listening. Bye-bye.
Thank you, Lorenzo. So we need to be sharp. So Paul and Sarah, you have just 5 minutes to discuss your presentation.
Yeah, I will start. Is my camera on? Well, nice to meet you, everybody. My name is Paul. I am a PhD student at Utrecht University. I think I can start my video now. Okay, hello, everybody. So at Utrecht University, yeah, I'm a part-time researcher, so I also am a physics teacher in high school, which is a really cool combination, I think. At least it's never boring. So my research project is about a special relativity education at the secondary level, so at high school level. I think special relativity is a really nice introduction to modern physics because it does not necessarily require any advanced mathematics or any advanced geometry, at least not necessarily. I think what is required is for students to really think very deeply about some very basic concepts, such as how do we measure time, right? And if I have a clock here, if I want to measure the time coordinate of an event which is very, very far away, then how do we do that? Well, you need synchronized clocks, right? So I think for this topic, it is really important for students to think conceptually. So what we have done, I will try to share my screen. Yes, share it. So what we have done is we have started by analyzing all of the, or many of the existing studies on the topic. So we have written a literature review in which we collected and analyzed 39 articles about special relativity at the secondary and lower undergraduate level. And we have analyzed them for learning difficulties, teaching approaches, and research tools. So just very briefly, what really struck me is that looking at learning difficulties, students really have difficulties in understanding quite basic concepts, right? So, for example, the light postulate and the principle of special relativity, they are very, very deep concepts, and they are very difficult to understand if you do not have a very clear image of frames of reference. And especially the role of observers and events is quite abstract. And if students do not fully understand this, then it will lead to all kinds of misunderstanding and misconceptions. So that has led us to think, how can we facilitate students in this process of understanding these basic concepts? And we have come up with this idea to make a kind of a visual modeling tool, as you see here, where we support students in performing thought experiments. So we really want them to perform the thought experiments themselves. Okay, so they can place objects such as cars or rockets or whatever onto this grid and assign velocities, and then you can see the trajectory from various frames of reference. So in this way, yeah, we hope that we can engage or we can simulate active engagement of students with this topic. I think I will keep it short for now, but I would just like to close by saying, if you have any comments or questions, I would really like to exchange some thoughts with you. Thank you.
Okay, thank you, Paul. Very, very interesting. Again, the power of visualization returns. So we have last panelist, that is Sarah. Sarah, if you want, you can share your connection.
Okay, yes. Do you see me? Do you listen to me?
Yeah.
Okay, I will be very fast. So I'm Sara Mattiello, and I'm a primary school teacher. My supervisors of my degree thesis were Professors Matteo Leone and Matteo Ruggiero. Our work takes inspiration from David Blair's researches, and in particular, we wanted to demonstrate that the children can approach to Einsteinian relativity. We investigated the role of a reference frame of Galileo's relativity, the speed of light, and the gravity as a space-time deformation using different methodologies like laboratory activities and thought experiments. The results were very positive since pupils improved the science skills and the motivation towards learning science in general. Broadly speaking, the current study work seeks to prove the effective possibility to integrate modern physics in concepts in the science curricula through a longitudinal path which starts from primary schools and continue in middle school, high school, and maybe university. In fact, the years of primary school are a crucial moment of growth in which it is possible to create the principal mental structure vectors of future learnings, according, of course, to the Brunner's spiral learning theory. So to conclude, we firmly believe in the Einstein First project, and we are trying to reply the experiment to extend the cross-section and to prove its validity. Thank you for your attention.
Perfect, Sarah. So, Magdalena, I think we are at the conclusion of this session. And as we said in the chat, we will have the possibility of sharing further idea during the session, next session on Thursday. So we can end for today. And,
yeah, I think that was just in time. Thank you so much for being really brief and short and presenting your amazing work. I know there could be more, or you would like to say more. Thank you all for being here. It's been so much fun seeing all of you and learning more about your work and your research. As Cedric just posted to the chat, our next session will be on Thursday, starting at 8 a.m. Central European time, so that our Australian colleagues can join. We are going to have 3 keynote speakers, and we will have another hour of plenary discussions. So I look forward to seeing you again on Thursday, and just wish you a beautiful evening or day. I think Matteo and I are going to have dinner. Some of you might have breakfast. We're going to see. But in any case, wherever you are, have a great day, and to see you next time.
Yes, I would like to thank our chairs and speakers for these wonderful talks and for running this live session so smoothly. Thanks to all attendees for participating today's webinar or live session. Thank you very much for your time. Have a nice evening or rest of the day, wherever you are around the world, and take care and stay safe.